Joe?
Hi, everyone. Welcome. Thank you. I hope you enjoyed the conference so far. So until now, you were all comfy in your chairs, enjoying the lectures. For this one, I hope you brought your boots, because we're going to get a bit messy. So welcome to Going All In on Serverless, Stories from the Trenches. All the things that you're going to hear are real-life stories from my own experience, and I hope it will help you as well. So before jumping into the trenches, maybe let me introduce myself real quick. My name is Barak. I work at a relatively early-stage startup named Vox. And our mission is a world where people can do more with voice. So if you feel like this is a mission you can relate to, and you believe in the power of voice to improve our daily life, and if you want to build things from scratch with me, feel free to contact me right after this lecture. So what's on our agenda for today? So we are going to hear a tale about a development group that tried to go all in on serverless. We will talk about the motivation, why we decided to try and go all in on serverless, how we did it, and how did it end up. And hopefully, you will be able to learn from that a thing or two on your next journey. So let's get into the story. So we were a small startup, and we started from scratch. And that's like the best position to be at, right? That decisive moment where you started at a blank page, and you need to decide, OK, what stack I'm going to use, what's going to be my architecture. And in that very defining moment, we said, OK, let's do it all serverless. But why would we do such thing? Why would we go and decide to go on everything to be serverless? So obviously, because it's cool. At least back then, it was cool. All the cool kids were writing blog posts about serverless. And it seems really cool. But cool, I guess, is not a great engineering case for making a decision. So we went to find a better engineering reasoning to do it. And we said, infinite scale. Like, the first thing a startup needs to think of is that day of Black Friday where all its customers will try at once to reach our servers, and then they will all collapse. So we must prepare for that day. Well, I guess that's not the first thing you need to worry about when you start a new startup, when you decide about your stack. So why really did we do it? Well, first, we were a small team, and we wanted to keep it focused and to be made of only full-stack engineers. We didn't want DevOps. We wanted dev velocity, because the first thing you want as a new startup, and you have a lot more to build than you can actually do, is to make sure that your stack keeps your velocity very high so you can create lots of things really fast. And then also, we were working on a pretty wide product, which had many aspects to it. So we knew we didn't want to be worried about resources. We just wanted to keep spawning more and more services. Some of them will be neglected. Some of them will be used. But we just didn't want to be worried about that. We just wanted to keep on running and creating more and more things. And obviously, to achieve that, we knew we want and need CI/CD. And for that, we would need infrastructure as code. As much as we love clicking on buttons, we preferred it to be automated so we wouldn't have to repeat it manually. And a nice bonus for us as well was pay only for what we used. The more we grew, we will pay more, and we didn't need to start paying for servers that aren't being used by anyone. So having that in mind, we picked AWS as our cloud provider, and we were off to go to our serverless journey. But before that, maybe let's align on what does serverless actually means. So unless you have a code which completely runs on your client, obviously there must be a server. So there's no real such thing as serverless. But by saying serverless, what we aspire for is actually just to be able to build our applications without thinking about servers. So there must be some server somewhere at the cloud provider serving our requests, but we don't want to think about it. We just want to focus on our code. So first, let's add the two most basic building blocks to our toolkit, which were Lambdas. Lambdas is the compute solution for serverless on AWS. That's where we are writing our code, and it's going to be executed on the Lambdas, and that's where it would be executed. So that's the first block. And then the second one would be API gateway. So essentially, if we want our Lambdas to be accessible for the web and for our customers to be able to reach those Lambdas, we need to expose them to the internet, and the way to do that on Amazon is to use API gateway, which can be connected to our Lambdas. Then the next thing we had to do, as I mentioned earlier, CI/CD was a must for us. So we figured what's the easiest way to achieve CI/CD. And we found out, OK, there is this cool open source framework called Serverless framework, which essentially gives you a configuration files that will be able to provision your code, so you won't waste time making clicks on cloud providers. And it's lovely. Like, look at that amazing a few lines of configuration, and we already had our first Lambda. And then the next thing was, OK, how can we expose it to the web? So again, adding a couple of more lines of code, and now we added HTTP API, the path for our Lambda to be accessible from which method, and voila, we have an accessible Lambda that can be accessed by our customers. And lastly, we wanted to deploy it. So Serverless framework brought us both the configuration file and the way to deploy it. So it was basically as easy as running serverless deploy, and our Lambda is already on its way to our cloud provider. So far, we got really the basics real quick, and it's worked great, because without much effort, we managed to achieve infrastructure as code, have a super easy way to deploy it, and it's CI/CD ready. Amazing. And that basically was our honeymoon phase. We were sure we were on the right path. We knew that we made the most brilliant decisions, and our cloud infrastructure looked almost at something like that. So we had the users, the API gateway, everything is on Lambdas, and we were happy, living happily ever after. But like most of honeymoon phases, not all of them, but many of them, pretty soon enough, trouble came. And the first issue we encountered was that our response time for our users was a disaster. Like, we could see some requests that would take over a second, which is ridiculous in a world where you expect everything to happen in a couple of milliseconds or hundreds of milliseconds. And we started at the network and not understanding which code we wrote so horribly wrong that it would take sometimes a few seconds and sometimes none. So we tried to think, how can we debug it? So luckily for us, we weren't the first one to encounter such thing, and AWS already thought about it. So AWS added a tool called X-Ray. X-Ray is a tracing platform on AWS that allows you to observe and debug your code as it runs through the cloud, and gives you visibility how much time was spent on each part. And it looks something like that. So the dashboard is basically, you can see all the requests that were involved in order to, around the cloud, in order to fulfill a specific request, how much time was spent on each part, and diagnose the actual issue. Also nicely, it can give you a nice diagram showing all the resources that have been called. And again, luckily for us, serverless framework worked great. So enabling this tracing was as easy as adding another line of configuration, and we already have a tracing in place. So now we can start understanding what's causing that nightmare of response type. And digging hard enough into X-Ray, we realized that whenever you invoke a Lambda, you can see that a few parts consisting the actual time it took. So in this example, we can see 1 second spent in the initialization phase, but the execution took 2 milliseconds. And then we tried to figure, OK, so what does initialization phase mean? So it's more commonly known as a cold start. So essentially, we said there are no servers, but there are servers. We just hoped not to think about them. So essentially, whenever a new request is being made to the cloud have to provision resources for our code to be executed. And whenever those resources are not ready, usually because of our traffic is not stable enough. So either there wasn't enough traffic lately, so it needs to provision new resources, or there start to be a ramp up in our communication, meaning that there need to be more provisioned resources to be able to fulfill the requests. On these occasions, we will hit cold starts. And then to understand how can we optimize cold start, we need to understand better what does cold start mean. So basically, this is the life cycle of a Lambda. So the first step in case of a cold start, it will have to download your code. Then it will have to start a new environment to execute the code. In our case, it was Node. And lastly, it will have to execute the initialization code, like any server that we have. So there's the parts of the code that are executed and our request handler, but there's the part that needs to be executed when the server fires up at first. Usually, when servers world, we don't care about the init code because it will run only once or maybe on rare occasions of auto-scaling, but it's not something that we bother about. So then we started to understand how can we optimize those steps and where the problem lies. So first one would be familiar for any front-end developer in the crowd, optimizing our code. So that's the first problem for a front-end developer. You create your bundle, and then you realize your code takes too much, and it takes too long to download, and now you start to optimize it. So yes, literally in real life, we started adding Webpack for our server components in order to try and optimize their code. So if you're not familiar with Webpack, Webpack is basically a bundler that is able to combine your JavaScript code and try to optimize it and minimize it. So we added Webpack. And again, luckily for us, we weren't the first one to encounter this. So coming again for serverless framework, there was already a plugin that allows you to connect Webpack to your deployment phase and to make sure that it will run Webpack build before it's deploying our code to the Lambda, to the cloud. And then the next thing we try to understand better, even given the fact that we have Webpack and we reduced our own code, now again, a common issue for any front-end developer that will shake his head right now is that we start to investigate which packages that we use are taking too much. And sadly for us, unlike the front-end world where nowadays every package is being measured by what is its size and how tree-shakeable it is, meaning how easy it's to eliminate code that you're not being used. The Node ecosystem is not there yet because it didn't have to worry about any of it until now. So we were making some progress here, but we still understood that there are some parts that are beyond our option to optimize. Coming back to the second phase of a cold start, that's the code initialization phase. So we were using GraphQL. Obviously, I won't get into details about GraphQL now, but the one thing that you should know about GraphQL is that the initialization of a new GraphQL server is intensive because it will have to read the whole graph definition and only then will be able to execute new requests. So that can be both CPU intensive and can take time. And we realized that that's something that is putting weight on our Lambda initialization. So then we thought, okay, can we increase the CPU of Lambda to make that one run faster? So the answer, it is possible, but not directly. So you can control directly about the CPU of your Lambdas, you can control about the memory. And there is obviously some sort of correlation between the memory and the CPU. So increasing the memory of our Lambdas really helped reducing that initialization time. And again, using the fabulous serverless framework, it was as easy as adding another line of configuration. Lastly, the best way to fight cold starts is to make them not happen, right? If there aren't any cold starts, then we don't need to deal with all these issues. And luckily for us, and to be honest, many of these tools were introduced along the time that we were working, so that they came along as we worked on our architecture. And Amazon introduced a new concept called provision concurrency, which basically means So, we said you will pay only for what you use, but if you want to make sure it's faster always, you can tell us to provision a certain amount of lambdas that will always be ready, regardless of your traffic, and in that way, you will reduce the chances of hitting cold starts. So as you can see in the chart, which is an example from AWS documentation introducing provision concurrency, it can significantly improve the chances, the overall request time, because it reduces the chances of hitting cold starts. And luckily for us, serverless framework for the Savior, and it's also another line of configuration saying, okay, I want for this Lambda 3 provisioned concurrencies, and that's really helped us improve also the request time. Okay, so we did quite a lot. It starts to get, we already got a bit more complicated than our honeymoon phase, but now we were much better. Our Lambdas were warmer, we were staring again at the sun, and everything felt better. But then we faced some other issues. So remember when we started, we talked about infinite scale, right? So we don't need to think about scale anymore. It's serverless. So that's true for our compute part. But our compute part needs to communicate with other parts, right? We need some storage somewhere, and that storage will be communicated with our Lambdas. And we picked Postgres as our database solution when we started. And Postgres, like many other SQL-based databases, one of its caveats is the fact that it takes a lot of time to initiate connection with it. It requires handshake to start the connections, and that's why you usually will have a connection pool. That connection pool will be initiated whenever you start your server. It will keep a few connections always ready, so the next request will be fast. But now it's a bit of a problem because we don't have that state, because our scaling is basically, now if we have a peak of connections or a peak of requests from our customers, that will spawn a lot of Lambdas instantly. And we started with each Lambda having its own pool. Now, when there are these spikes in communication, each Lambda creates new pool. You will exhaust your database connections real quick. And that's what's happened to us. So we started seeing tons of DB connection errors because each time we will have scale, we will exhaust our database. And that's not a metric from our example, but this is like from a thread that I found on Stack Overflow when someone shows the impact on his database when he moved from server to serverless and how it's affected the spikes in connections to its database. But luckily for us, AWS already knew that. They already were aware of this problem, and they introduced a new tool. So if you didn't notice, we start to stack lots of tools to support our very simple and nice serverless promise. So that's a tool called RDS Proxy. So RDS Proxy is basically a proxy in front of your database that you will point your connection configuration to it instead to the database, and it's basically a component that will manage the connection pool for all of your Lambdas. So it will keep the state, it will keep the connection pool, and then not every Lambda will create new connection. That way, we won't create that crazy amount of load on the database, and our Postgres DB can live happily along on our Lambdas. And that's helped us a lot. So maybe it's a good time to recap on what we did so far. So we improved the Lambda download phase using Webpack, which also added tree shaking. We improved the Lambda initialization phase by increasing the Lambda memory. We added X-Ray as our tracing platform to be able to track and understand how much time is being used on each part on the cloud. We fixed the DB connection issues by using RDS Proxy. And we provisioned our Lambdas to reduce the actual chances of hitting a cold start. So now we can take a rest and enjoy our amazing serverless infrastructure, right? What do you think? Will it work or it won't work? I can't hear you. OK, some say work, some say it won't, so let's find out. So actually, while we really improved our situation and we thought we were good, we still had some performance issues. But now these were already more specific to specific use cases that we had. So what were our weak links? Why, despite all this effort, we weren't able to get to the results that we hoped to achieve? So first, our stack, when we started, we didn't think about our stack in terms of its impact on serverless. So we went with a very heavy stack code-wise. We were using SQLize ORM as our ORM library, which is a huge library, which is very big and very hard to tree-shake. And we used GraphQL, which again, big library requires other big libraries. So while we added Webpack and we improved the download phase, it still wasn't good enough because of the stack decisions we've made. Secondly, we made a very bad decision, which I guess is kind of bad in general. So we had many requests which triggered a lot of lambdas in chain. And whenever you have many requests that doing a chain of lambdas, you significantly increases the chances of cold start, right? Because now only not the probability of the first lambda to hit a cold start, the second one, the third one, and the fourth one, and the more lambdas that you call on each request, you increase your chances of hitting cold starts. So basically, these two reasons, along with the fact that we used lambdas for our most critical facing flows. Actually, our payments, like when you hit the payment button, it will hit a lambda. You can think about how frustrated user can be at this phase where he uses his wallet to pay you, and it takes forever. So the combination of these three was really dreadful for us, and that's when we decided to go hybrid. So now what does hybrid means? How would it look like? So it would be, again, oversimplified, but it would be more or less something like that. So we said, okay, we did love serverless. We did get amazing developer experience working on serverless. But we can't afford the penalty it causes to our customers. So let's make sure that everything that is user-facing will be not on serverless or on some sort of cluster. We use ECS, which is the Docker orchestration of AWS. And anything that is async, we feel great about having it on Lambda. So anything that is coming from queues, that needs to run on some periodic times, all of these works great for the serverless use cases and using Lambdas. But anything that is critical and facing our customers, we still had to start managing our own cluster. And that one, for real, worked really well, and we quite enjoyed it. So what did we learn so far from this experience? So first, working with Lambdas was great for dev velocity. It was really easy to set up the CI/CD. It was really easy to monitor, and was really fast to deploy, spawning new environments. All these kind of tasks were super easy, and we liked it. Again, like I said earlier, it's work great for sync flows. For async flows, it's not that great for sync flows. But it can work for sync flows as well if you plan ahead. So again, if you decide to go with Lambdas for synchronous flow, prefer lightweight libraries that won't have a heavy footprint or initialization. And most importantly, make sure that you avoid having any sort of chaining, and make sure that at most it would be one Lambda for each request. If you are able to comply with these two, I think given the solutions we saw so far, you can get to pretty good results and still enjoying the dev velocity of serverless. And lastly, we covered a lot of tools over this talk, which you can remember and use in your future journeys. So we talked about X-Ray, we talked about serverless framework, we got to new Lambdas and API gateway, RDS proxy to avoid the DB connections, and Webpack to minimize our code. And that was it. So thank you.